Hi team, my name is Ruturaj and we'll be discussing dependency blast radius simulator. This video is demo walkthrough of basically five component we'll be discussing, which is architecture overview, feature walkthrough, application flow, example execution, which is demo, live demo, and key design decisions. Why I took this decision, why I took this design, and what are the future enhancements we can do in this design. So let's discuss architecture of this project. System has three layers. At the top, the front end, a Next.js React app running on the port 3000. In the middle, the back end, a Node.js Express API on port 5000. At the bottom, there is a data layer, PostgreSQL for persistent storage, and Redis for real-time messaging. They talk through two channels. First is REST APIs for normal request and WebSockets for real-time up. This is the most important part. Let me trace what actually happens when a user simulates a failure. Let's say someone clicks fail payment gateway. Step one, which is the React frontend sends post request to slash API slash simulate with service ID. Moving next, the back like the Express backend receives it and call the graph engine. First, it loads all the dependencies from the PostgreSQL in single query, not one query per node, one single query, and it builds an in-memory adjacency list. Then moving next, it runs BSF breadth-first search on that in-memory graph. BSF explores in rings. First, services directly depending on the payment gateway, and then services depending on those services. It keeps on going until nothing left to explore. This gives us the full blast radius and exact cascade depth. Moving next, it calculates the severity score from P0 to P3 based on how critical services were hit and what percentage of total system is affected. Next is the result gets stored in simulation history table in PostgreSQL, then published to Redis pops up. And then Redis pops up relays that message to socket IO, like which broadcasts it to every connected browser tab in the real time. So if another engineer has the dashboard open, it gets updated on real time, and there is no need to like page refresh. Moving next, the graph engine has five algorithm, each solving a different problem. First is BSF for blast radius, uh, answers what breaks when something fails. DSF, DSF with three color marking for cycle detection. When you try to add a dependency, it checks if that would create a circular loop or blocks it before saving, right? Next is PageRank. PageRank is applied, it's a Google algorithm which is applied to our service graph to find services that are architecturally critical, even if they are not labeled as critical by human. Next is Tarjan's algorithm for finding a single point of failure. This is an edge case which our DSF and BSF will miss in future if the system get complex. So we use Tarjan's algorithm to find out a single point of failure in the system, uh, whose removal would split the graph, right? The next is it's an optional but still I implemented, which is Monte Carlo simulation for chaos engineering. Instead of saying everything definitely works, it runs thousands of iterations where each dependency has a reliability score, giving probabilities like, for example, like auth service has 73% chance of failing if payment gateways goes down. So Monte Carlo simulation just gets more deterministic instead of getting predictive. So that's why Monte Carlo simulation supports the decision and it gives a better result. So these are the features list which I have implemented. On the left hand side, there are 12 core features which were expected on in the rubric of the assessment PDF. And on to the right side, there are features which are core implemented by me. So you will notice all the features in the live demo which I'll be showing moving forward in this video. Uh, So let's start with the service management on the right panel. I can create services. Let me create one. Each service has a name, owner, and criticality level. The criticality matters because it directly affects severity scoring during simulations. Now let me add a dependency. I go to dependency manager and link API gateway to auth service. You can also search and filter services. For example, if I filter by critical, I only see just critical services. I also can filter by team owner teams. Notice the graph updates in real time. There is a new edge, and if I try to create a circular dependency, it makes an auth service depend on, like making an auth service depend on something like eventually depends on back on the API gateway. Watch what happens. It blocks it and shows me exact cycle path that TSF with three color marking running on back. This is a layer layout services with no incoming dependencies sit at the top and downstream services cascade below. I can drag any node to reposition it. The graph renders using customers SVG. Each node shows an abbreviation, full name below, and colored border based on the criticality. Red is critical, green is normal. This is the main feature. Let me simulate a failure. I will click on a critical service, say payment gateway. To select it, the dash circle shows it selected. I can select multiple services for simultaneous failure. Now I click on simulate failure. Look at what happens. The failed service turns red with failed batch. Impacted service turns orange with a depth number 1 means directly impacted and 2 means second level cascade. The dependency edges that carried the failure turn red and dashed. A severity badge appears on the graph. This one is P1 means severe. Uh, Below the graph, the damage report shows everything: service hit, cascade depth, how many levels of failure traveled, critical down, how many critical services were impacted, resilience gauge, and animated scoring to show system health. Service impact heat map shows every service status. If I click on the impacted service like order service, it shows me the exact dependency path. See the payment gateway, checkout, orchestrator, or order service. That's the exact chain that caused order service to fail. It tells me the this service fails because payment gateway went down, cascading through one immediate service. That's the dependency path exploration feature. After every simulation, the result is sent to Grok LLM, specifically Llama 70 billion parameters LLM, for an AR-powered incident analysis. It generates sections like root cause analysis, cascade analysis, business impact, and mitigations. The AI isn't generating generic advice, it references specific services names and cascade chains from this simulation, and it's optional. The app works perfectly without it. Most services work with 5, 6 services. Most demos work with 5, 6 services. Let me show you this at production scale. This loads a realistic e-commerce platform, 120 plus microservices across the 14 domain teams, gateway or payment orders, and many more. And it uses completely separate database tables, so it never touches your main data. I can browse by domain. Let me expand payment team. I see payment gateway, Stripe adapter, fraud detector, etc. Then the ego graph shows payment gateway and two hop neighborhood. Uh, I run the simulation and the cascade hits 30 plus services across the multi-domain. The chain shows exactly how payment get. I can select multi services too. Let me just select auth service. With two critical services down, the blast radius is now P0 incident. The analytics tab shows the trends across the simulations. I have run the impact over time chart shows how blast radius changes across the simulation runs. The risk radar profile shows which services appeared most often in the blast zone. The services breakdown table rank every service by frequently it was used and it was impacted, how many times it was source to a failure and its dependency count. The history tab has time machine. I can use the slider to replay any past simulation and see the graph state at that point. Every simulation is stored in PostgreSQL with timestamps. Now the key design and decisions are, let me wrap up with the key designs and decisions. PostgreSQL over MongoDB because our data is relational. Services depend on services, foreign keys and on delete cascade gives us integrity. BSF for blast radius, DSF for cycle detection, and each algorithm is matched to its problem. BSF gives us shortest path and depth levels. DSF gives us cycle detection. Custom SVG graph instead of graphing library. This gave us full control over how failed impacted nodes render, drag behavior and animation. Redis as optional infrastructure. The app degrades gracefully if Redis is down. Socket IO broadcasts directly. The core feature never break. Isolated scenario tables. The production scale demo uses separate tables like scenario services, scenario dependencies, so it never corrupts the user main data. For testing, I have unit test for BSF, DSF algorithm, page rank algorithm, articulation points, and Monte Carlo simulation. Thank you for watching. I am excited to discuss this discussion of any of these decisions further.